Hey class, it's Mr. M again. Here we're looking at how you can determine relative extrema from a graph. So I've drawn a generic curve here, nothing special about it, it's not even drawn very well. Sorry. Anyway, we want to figure out what we can determine about the function f, which we do not see from this graph of its derivative. Alright, well, there's a couple things we can notice. One is these locations here, the roots, so to speak, of the function f prime. What would the term be for these points? What's a word that would describe these locations? I want you to pause the video and think about that for a second. And hopefully you've unpaused it and thought, and the correct answer is these are critical values or critical numbers. Because these are where the derivative is equal to 0. Okay. Well, on a number line method, or using the first derivative test, we know that if you have to have a change of signs from positive to negative or negative to positive, in order to have not just a critical number, but indeed a relative maximum, or relative minimum, as it were. So let's look at this first point here. I'll label these points A, B, and C so we can refer back to them. At point A, you have a value of 0 in the derivative, and before A, you have a negative value, and after A, you have positive values. Now, notice that it's increasing all the way through. That's a different story. That'll talk to you about concavity, which we aren't quite at yet. For the moment, though, you have negative numbers and then positive numbers. Well, on a number line, this would tell you that this is decreasing and then increasing. And when you have decreasing behavior in f and increasing behavior following a point in f, if you travel through 0, meaning you have a differentiable point or a continuous derivative, which we do here, therefore this would be a minimum, a relative minimum. You go from negative to positive, passing through 0 on the derivative, which is what we're dealing with here. Here, you also have a slope of 0 a value of 0 in the slope function, right? All of these tell you about the slope of f, which we do not have a picture of. Before you get to point B, you have positive values up here. Granted, they're going down, but they are positive. And afterward, you have negative values. So positive above and then negative below. You go from up to down, which tells us that f is increasing and then f is decreasing, which therefore tells us that this point at point B is a relative maximum. It goes up and then it goes down, positive to negative. And finally, point C, well, if you've kind of studied what's happened here, you can almost quickly recognize you have a value of 0. It's going from negative to positive, and when I say it, I mean the value of the derivative. And if the derivative goes from negative to positive, the function is going from decreasing to increasing, or down and then up, and this would also be a relative minimum. And there you go. You can determine critical numbers by looking at the roots of the derivative. You can therefore determine if any of them, in this case all of them, are relative extrema by looking at the way in which it passes through 0. This is one way to go through 0, negative to positive. This is doing the same thing, negative to positive. This point, however, is going through 0 in a different manner. It's going from positive to negative, which is a maximum. Okay, let's take a look at another graph. Alright, this one isn't drawn any better. Poor me. Sorry about that. My unsteady hands, as you can see, are on the values of 2 and 3. But I want you to pause the video for a moment and ask yourself where you have relative extremes, where the relative maxes are and where the relative minimums are in both of those cases, if you have any at all. Okay, hopefully you paused it and you've unpaused it now, and now we can take a look at whether or not you were right. Well, critical numbers occur when the derivative, which is what we have here, is equal to 0. Looking at the negative region, They're never equal to 0. Again, the slope is equal to 0, it appears at a point, but the value never is, until you get right here. We'll call that point A. Now, I know the value is 3, but we're talking about just a generic curve here. And I intended for this, I didn't draw it very well, to be another point of 0, or another root, and we'll call that point B. So these are, once again, our critical values, or critical numbers. Well, as we saw a minute ago, you can pass through 0 in a variety of ways. You can go positive to negative, you can go negative to positive. Well, here we go from positive values to negative values, up and then down in terms of f, which again we don't have a picture of. So, since f prime goes from positive to negative, passing through 0, because this is a continuous curve, f prime is, therefore f is differentiable, that tells us that at point A you have a relative maximum, just like point B in the previous example. Let's take a look at point B in this example. Before you get to point B, you are at the negative value, you're below the x-axis. And after point B, you're still negative. You didn't go up here like was typically expected. You didn't go above the x-axis to reach the positive values. You started negative, you hit 0, and you stayed negative. We did not have a sign change here. We started going downhill or decreasing, we reached a flat point, and then we continued decreasing. So this is neither a relative minimum or a maximum. Not a relative extreme. We don't know, or rather we do know, that before and after this point, there is no sign change from positive to negative or negative to positive. So this represents another way in which you could approach or have a derivative equal to 0, therefore a critical number, but a critical number is not always a relative maximum or minimum. And here's a clear example of how that would be. Alright, hope this helped.